All right, so you're solving a second-order differential equation. You're expecting two distinct solutions, right? But what happens when the math only spits out one? This is the classic repeated roots problem, and today we're going to crack it wide open.
Here's our game plan. First, we'll nail down exactly what this one-root problem is. Then, I'll show you the super simple rule to fix it. We'll even visualize what this new solution actually looks like before jumping into two solid examples. And finally, we'll wrap it all up with the key takeaway you need to remember.
Okay, let's get right to it. What is this problem we're trying to solve anyway?
So here's the deal. For a second-order equation, the rules of the game say you need two different, independent solutions to build your final answer. It's like needing two key puzzle pieces. If your characteristic equation only gives you one root, you're missing half the puzzle. You just can't build the complete picture.
And the culprit? It's the discriminant from the good old quadratic formula. Remember b squared minus 4ac? When that thing equals 0, the whole plus or minus part of the formula just vanishes. Your two potential roots collapse into one single repeated root. So sure, we get one solution, y equals e to the rt, but that just leaves us asking, where on earth is the second one?
So how do we conjure up this missing second solution? You might think it's some complicated, messy process, but nope. Turns out the fix is so simple, it's almost beautiful.
And here it is. This is the whole trick. You take the solution you already have, that e to the rt, and you just multiply it by t. That's it. That simple act gives you your second independent solution. And with that, we have our complete general solution. C1 times the first solution plus C2 times our new one.
Okay, I need you to lean in and listen close, because this is the #1 trap students fall into. When you need to find the derivative, which you will for initial value problems, you absolutely, positively have to use the product rule on that second term, the one with the t. Forgetting this is the fastest way to derail your whole problem. Don't do it.
So we know the rule, but what does multiplying by t actually do to the graph? Getting a picture in your head for how this thing behaves really helps build your intuition. Let's do a quick comparison. On the left, you've got your standard exponential decay. It starts high and just drops and drops and drops. Simple. But look what happens on the right when we toss that t in front. It's a whole new ball game. At the very beginning, when t is small, that linear growth from t is actually stronger than the decay. So the function goes up first, creating this signature hump. But don't worry, the exponential always wins in the end. It takes over and pulls the whole thing back down to 0.
All right, enough theory. Let's get our hands dirty and see this rule in action with a nice, clean example. Our first problem, y double prime minus 6y prime plus 9y equals 0.
First step, let's get the characteristic equation. That's r squared minus 6r plus 9 equals 0. Now you might recognize that. It's a perfect square. It factors right down to r minus 3 squared. That gives us a repeated root at r equals 3. Perfect. Step 2, we just apply our rule. The solution is c1 e to the 3t plus our new term c2 times t e to the 3t. And that's it. General solution, done.
Okay, that was the warm-up. Now for the full workout. Let's tackle an initial value problem where we actually have to hunt down those constants, c1 and c2.
Here's our problem. Y double prime plus 4y prime plus 4y equals 0. And this time we have starting conditions. At time 0, the position y is 1, and the velocity y prime is 5. You know the drill by now. The first two steps are exactly the same. The characteristic equation is r squared plus 4r plus 4 equals 0, which, hey, is another perfect square, r plus 2 squared. This gives us a repeated root of r equals -2. So we apply the rule, and our general solution is y of t equals c1 e to the minus 2t plus c2 times t e to the minus 2t.
And now for that all-important step we warned about. We need the derivative. The first term is easy enough. But for the second term, we bring out the product rule. Let's break it down. It's the derivative of the first part, which is just c2, times the second part left alone. Then you add the first part, c2 times t, times the derivative of the second part. We clean it up a bit, and there's our full expression for y prime.
Now for the satisfying part, plugging in the numbers. We start with y of 0 equals 1. When we plug t equals 0 into our solution, that whole second term with the t just goes to 0. Poof. And e to the 0 is 1, so we're left with c1 equals 1. Awesome. Now for y prime of 0 equals 5, we plug t equals 0 into our derivative. Again, the term with the t disappears. We're left with minus 2 c1 plus c2 equals 5. We already know c1 is 1, so
minus 2 plus C2 is 5, a little bit of algebra, and we get C2 equals 7.
And there we have it. We just plug our shiny new constants back into the general solution, and we get our final, specific answer. Y of t equals e to the minus 2t plus 7t e to the minus 2t.
Okay, we've gone from the why to the how to the what if. Let's take a step back and boil this all down to a simple checklist you can use every single time. Here's your 4-step playbook. 1. Find your root and make sure it's actually repeated. 2. Immediately write down the general solution using the multiply by t rule. 3, and I'll say it one more time, if you need the derivative, always use the product rule on that second term. And 4, use your initial conditions to solve for your constants. That's the whole process, right there.
So, there you have it. You are now fully equipped to handle any repeated root problem that comes your way. But our journey isn't over. We've seen what happens when the discriminant is positive, giving 2 real roots. We've now mastered what happens when it's 0. So what's left? What happens when it's negative? Well, that's when things get really interesting and we enter the world of imaginary numbers, and we'll tackle that next time.